So yesterday our session ended with introduction to spice. So we did write something about spice as follows: that spice is an abbreviation of simulation program with IC emphasis. It is a programming language used for simulating circuits expressed as an interconnection between components which can be active or passive or both. Then we need a spice engine to run a spice program. Spice engine is written in Fortran language. Spice engine uses nodal analysis to find voltage and current values. Spice is a concurrent language similar to VHDL. Language has a rich library of keywords to represent resistor, inductor, capacitor, diode, SCR, BJTs, MOSFETs, dependent and independent voltage and current sources. It has the ability to perform DC analysis, also known as operating point analysis, AC analysis, transient analysis, noise analysis, and much more. And last, we told that it uses a model library which contains the complete model or behavior of every possible component. And we had mentioned that all the circuit simulators such as Multisim, Proteus, or whichever others are available, they all use the spice engine for generating the simulation waveforms for us. So we take our discussion ahead by learning to write simple programs. Well, again, as I told you in the beginning of the semester, that yes, VHDL is a language, but whenever you write a VHDL program for any digital system, we do not say write a VHDL program. We say write a VHDL model. That is why we will not say write a spice program. We will say spice model. So we have VHDL modeling, we have Verilog modeling, we have system Verilog modeling. Similarly, we have spice modeling. So we are going to learn to write spice models for very simple circuits which you must have studied in your first year of engineering, wherein there is some current division happening or there is some voltage division happening. Okay. My OneNote screen is visible to you?
Yes, sir.
Yes, sir.
Okay. Okay. So rather than going into the theory, we can directly take examples of spice modeling. Okay. So the first thing which we write here is although spice is a language and that it can be used to write a spice code or program, the correct term to be used is spice model. Okay. So although spice is a language, the correct term to be used is called as a spice model. So we say write a spice model for the circuit below. Okay. Hence we shall use write a spice model for the circuit shown below. Okay. So if you remember when I started teaching you part B of VLSIDT practicals and that we got introduced to the Microwind tool, I told that the correct starting point for making the layout of any CMOS system is to make the transistor level schematic of the system and then to terminalize the circuit, that is indicate all the three terminals of MOSFET, that is drain, gate and source. Similarly, what you need to do to write a spice model for any circuit is to nodalize a circuit. I repeat, nodalize, that is indicate the nodes. Now we have taken a task which says that write a spice model for the circuit shown below. Okay, so let us first draw the circuit, then we will learn how to nodalize the circuit. So say for example, my circuit is like this. I have a source, I have one resistor and I have another resistor. Okay, so this is the circuit given for which I have to write a spice model. Only thing which is there is, it has been given to me, this is 1K, this is 2K and this is 1 volt. What is expected is to find out the voltage drop V1 and the voltage drop V2. This is what is the task given. So I am going to nodalize the circuit. Nodalize the circuit means you have to define distinct nodes in the circuit. You have to give names to all the components. So now we are seeing here that I have the first component in the circuit, which is the voltage source. The second component in my circuit is a resistor of 1 kilo ohms, and the third component in my circuit is a resistor of 2 kilo ohms. So what I do is I will redraw the circuit and then I'll nodalize the circuit, right? Redrawing the circuit now. So I have to identify how many unique nodes are there in the circuit. Okay, so a node is any point in the circuit or a network where there is either voltage drop starting or a current division happening. So I can distinctly say that this is one node, this is another node. Okay, because there is a component in between these 2 points. I said these two nodes are distinct. So I can say let this node be node 1, that let this node be node 2, and as such you know that this is actually reference, or we can say it is ground. That is why we say this is actually 0, or we can also say it is ground. Okay, similarly I will say let this voltage source have the name V1 and its value is 1 volt. Similarly, let this resistor of 1K have the name R1. Similarly, R2 value is 2K. So first we verbally read the circuit. How do we read it? we read that the voltage source V1 is connected between node 1 and ground and its value is 1 volt. Similarly, I say that the resistor R1 is connected between node 1 and node 2 and its value is 1 kilo ohms. Similarly, I say that the resistor R2 is connected between node 2 and ground and its value is 2k. Is it okay? So now in the SPICE language, there is a certain order in which you are supposed to um, write the name of the component, its value and the node. So basically I have to tell this thing that the source V1 is connected between 1 and ground and its value is 1 volt and it is DC. Resistor R1 is connected between node 1 and 2, its value is 1k. Similarly, resistor R2 is connected between node 2 and ground, its value is 2k. See how I write it. Okay, so it is like this. So there are different syntax which are predefined in the language for defining sources, different syntax for defining passive components R, L and C, and also there is a different syntax for defining a MOSFET. We will cover that today. Okay, so understand one thing, that there are at least 5 steps to be followed in order to write a complete SPICE model. I repeat that there are at least 5 steps which are needed to write a complete SPICE model. Just like I told that there are compulsorily 3 building blocks of any VHDL model. First is library statements, second is entity declaration, and third is architecture body. Similarly, in order to write a SPICE model for a very simple system like what is there in front of us, we have to follow 5 steps. So first we'll write the 5 steps. Okay, so I can say steps for writing a SPICE model. Okay, step number 1 is define all components. These components can be active components like transistors, or they can be passive components like R, L and C. The second step is define all sources. These sources can be either voltage or current or dependent or independent. Okay, the sources can be voltage or current. They can also be independent or dependent sources. Third step is define the type of analysis to perform or to be performed. Many options available. It can be operating point analysis, it can be DC analysis, it can be AC analysis, it can be transient analysis, it can be noise analysis also. The fourth step is include the model files. So including model files in the SPICE model is similar to adding libraries and packages to a VHDL model, or saying hash define, or include stdio.h, include conio.h in a C program. So include the model files, and fifth and most important is define the type of outputs you want to observe. Okay, so the 5 steps for writing a VHDL, I'm very sorry, the 5 steps for writing a spice model are: first is define all the components, second is define all the sources, third is define the type of analysis to be performed, fourth is include the model files, and fifth is define the type of output. Okay, so define the components, define the sources, define the type of analysis to be performed, include the model files, and define the type of outputs you want to observe. Okay, now if you want to demonstrate how these 5 steps are observed in writing the spice model for the circuit above, it is like this. Okay, so please remember that we have 3 components here. We have a voltage source whose name is V1, its value is 1 volt and is connected between node 1 and ground. Second component is a resistor R1 connected between node 1 and 2, value is 1 kilo ohm. Third component is resistor R2 connected between node 2 and ground, value is 2k. See how I define them. Okay, so I say now this is a comment in the spice model. Okay, so I can say asterisk, I can say spice model starts here. Okay, now remember that I have to define V1, R1 and R2. Okay, out of these are components and this is a source. So what is our first step? Our first step says that define all the components, active and passive. So out of the 3 components V1, R1 and R2, the components are R1 and R2. See how I define them. I will say R1 resistor is connected to 1 and ground. So I will say R1 space 1 space ground. I will say 1k. So it is component name space node, first node space second node space value. Similarly, R2 is connected between 2 and ground, value is 2k. So I write it like this. I will say second component R2 connected between node 2 ground, value is 2k. So this is our step number 1, that is define all the component. Now we define all the sources. How to define the source? Now you know that the value of V1 is 1 volt and it is connected between 1 and ground. How do I define this? Like this. I will say V1 is connected between node 1 and ground and its value is 1. Okay, so when I say 1, how does it indicate that 1 is volt? From here. Okay, so this is this alphabet V. This alphabet V is actually the prefix for a voltage source. Okay, if I want to define a current source I1, I should use the alphabet I instead of V. Got the point? So in fact, V1 can be written like this. I can change this. So now if I say that the name is V in, then I have to write down VV in. Okay, I have to write down VV in. So I will say the alphabet V, which indicates I am going to define a voltage source, and I will say V in is connected between node 1, ground and 1. Many a times you can also write DC, but if you do not write DC here, it already assumes that it is a DC source. You can keep this. Okay, clear? Now I will highlight which are the keywords here. So GND is a keyword in the language, ground. Similarly, V is a keyword. Similarly, DC is also keyword, and all other things are user defined. Yeah, also K is also a keyword. K means 1000, 10 raised to 3. Okay, so all the things which I've highlighted in yellow color are all predefined keywords in the language. Okay, so now step number 1 is over. Define all the components. Second, I have defined the sources. Now I go to the third step. Define the type of analysis to be performed. Now what I want to do is that I want to find out what is the drop across R2, and also I want to find out what is the drop across R1. That is what my aim is. Okay, that is called as operating point analysis. So now what I do is I simply write .op. This becomes my step number 3. And understand one thing, that .op is also predefined. Dot is also defined and OP is also defined in the language. Fourth is include the model files. Fine. So here as such register is a very simple component, so you don't need to define any model files, but I will just tell you that what is the way to define a model file. So we have to say, either we can say so we can say dot include dot include and we can say file underscore name dot text. Another way is to define like this. If you are going to write a spice model for a CMOS array, you can say dot model, and you can say library link name, library link name, then library name, and we will say level equal to something. Okay, it can be 1 to 49. Okay, in this which are the keywords? The keywords are dot include, this is a keyword predefined. Dot model is a keyword. Library underscore name is also predefined like your library IEEE. The word level is also predefined. So this forms our step number 4, that is defining the model files. And last, we can define the type of output that you want to observe. So we can write just like this. We can say dot print v bracket 1 v bracket 2. Okay, so here this is the step number 5 where I have defined what kind of outputs I want. So here dot print is again a keyword, v is a keyword, again v is a keyword, and 1 and 2 means you just print what are the voltages at node number 1 and 2. So I'll make a comment here that say 1 and 2, they are the node numbers. Okay, it's very clear. that if we solve this, then according to potential divider rule, my voltage across V1 will be 1 upon 3 into 1, which will be 0.33 volts, and my voltage across R2 will be 2 upon 3 into 1, which will be 0.67 volts. Okay, so V1 comes out to be 0.33, V2 comes out to be 0.67. But then what is the potential at node number 1? Who can tell me? What will be the potential at node number 1 and potential at node number 2? What is the potential at node number 1?
1 volt.
1 volt. Very simple. So here we have 1 volt and here I have 0.67 volts. Now there are certain open source tools available which accept a spice model as an input, and directly they will give you the outputs. So I am trying to use one tool called as WinSpice, which is an open source, but somehow I am getting some bugs there. So I'll give you a demo. So I am having some, yeah.
Sir, in the first line of the code, R1
Yeah.
is connected with 1 and 2.
Yeah, I'm correct. You are right. Okay. So it is between 1 and 2. Yeah. So we will change this now. One and two. Fine. Okay. So now correct. So I cannot highlight 2 because 1, 2, R1, R2, all of them are defined by me. So I am not highlighting them and writing in them in black color. Now I think so it is okay. So actually when I run this model in a proper Spice engine based tool, so what I get is this. Okay. So what are the outputs obtained when I run this code or when I run this model is outputs which are obtained come out to be like this. I get V1 equal to 1.0000000 e raised to plus 00. The second output which I get in response to the program is 6.666667 e raised to minus 1. Okay, this is what I get. So it's a simple example of a spice model which can be written. So I hope this is clear that we wanted to find out what are the voltages at node 1 and node 2, and we identified that this particular circuit has 3 components: Vin, R1 and R2. Among these three, R1 R2 we call them as components, passive components, and Vin as a source. The name of the source is Vin. So we defined there are 5 steps, and according to the steps we defined the components R1 and R2 in this way. We defined that R1 is connected between node 1 and 2 and has a value 1k. We wrote this in this way: R1 space 1 space 2 space 1k. So 1 and 2 represent that node 1 and 2. Similarly, R2 is connected between 2 and ground with value 2k. So I wrote it as R2 space node 2 space ground space 2k. Similarly, I have to define that Vin is a DC source with value 1 volt. So we write it as capital V, then Vin. So it is V is the alphabet which tells to the Spice engine that now I am going to define a voltage source. If it was a current source, I would write capital I here. So capital V, and concatenated to that it is Vin connected between 1 and ground. So Vin space 1 space ground space 1 is the value. This is again a keyword. If you don't write DC also, it is okay. Then we told what kind of analysis to be performed: operating point analysis. So .op is a predefined keyword in the language for defining operating points, for calculating operating points or quiescent values in the circuit. Then we have to include the model files. So if you are having the model written in a text file with the proper format, then you can say .include file name .txt. Or if you are trying to write a spice model for a CMOS or a MOSFET based system, you can write down dot model space library link name, library name, level equal to 1 to 49, and last step is define the type of output. I say dot print. Dot print means it is like, you display it in the form of a window, waveform window. V bracket 1 comma V bracket 2. V again indicates to the spice engine that I am expected to find out the voltage at node 1 and 2. So 1 and 2 in parenthesis indicate that node numbers. Now this is a very simple circuit, but we are not interested so much in that. We are interested in writing spice models for VLSI systems, that is writing a spice model for plotting the IV characteristics of an NMOS, or writing a spice model for plotting the IV characteristics of a PMOS, or writing a spice model for simulating an inverter. So in Microwind, you actually made the layout for an inverter. You applied a frequency of 5 gigahertz at the input, and you saw that how the system is complementing the input. Everything we have done. The same thing we can do even using spice modeling. Right, so it is a very powerful language. In fact, I can tell that some things which even layout editors cannot do, Spice has the ability to do that. That is why we say that Spice is a very powerful language which is used by PhD researchers to actually find out that if a certain system has used a certain transistor with certain technical specifications, then can I find in some way that if I change the width and length or the threshold voltage of a MOSFET to a certain level, what is the performance improvement which I will get? So researchers, they access MOSFET model files, um, and they have access to about more than 250 different MOSFET parameters, right? So the spice model for a MOSFET has become so evolved, so advanced, that there are 250 configurable parameters there, and this is called as level. So when I said what is this level equal to, so level equal to 1 is the most basic mathematical model of a MOSFET, and then as and when you go on increasing the levels from 1 to 2 up to 49, 50, 53, you start getting all the practical characteristics. For example, if you do the spice modeling of an NMOS transistor and you plot the IV characteristics, then you will see that when the NMOS is in saturation region, the plot will show that the drain current is becoming constant, indicating that in the pinch off region, the MOSFET is acting as a constant current source. But when I resimulate my spice model with level equal to 49, at that time, it starts considering all the second order IV effects such as channel length modulation. So channel length modulation effect, if you want to see, then in the spice model, what you have to do is that you have to increase the level of modeling. So more and more practical parameters of MOSFET are considered, and you get more accurate simulations. In fact, I did not get time, but even you can see channel length modulation in action even in Microwind tool also. I will show it to you today. So let us directly jump to how to write a spice model for plotting the IV characteristics of an NMOS transistor. So here we are. Our another task for the day is write a spice model to plot IV curves of NMOS transistor having size equal to 4 mu upon 2 mu. Okay, so it is very obvious that here we have already defined that the size of a MOSFET is equal to W upon L. So this particular problem is directly telling us that the width of the NMOS is 4 micrometers and the length is equal to 2 micrometers and its size is equal to 2. So we are having an NMOS transistor having size equal to 2, and we have told that theoretically for efficient operation of an NMOS, the size of NMOS should be equal to 1.5. So theoretically, the NMOS should have a size 3 microns by 2 microns, giving a size of 1.5. Now, let us start to write the spice model for this. So first and foremost thing is that just like we had the circuit here in place, we have to also draw the circuit. So we'll draw the circuit 2 times. First we'll draw the basic circuit, then we will rename the circuit, we'll nodalize the circuit, everything we have to do. So the most basic circuit, which or we can say experimental setup. So we have to draw the experimental setup for plotting the IV curves. Now we know very well here, we know very well that when we say IV curves, it means output characteristics. So we know that output characteristics of any MOSFET are IDS versus VDS for different constant values of VGS, right? So we get a family of curves. So output characteristics of any MOSFET are IDS versus VDS for different constant values of VGS, which we call as family of curves. So I know that I have to vary VGS voltage in definite steps and I have to keep VDS constant. Okay, so the simple setup would be like this. I have an NMOS. So I have drain, I have source, and I have body, and I have gate. So this is the 4 terminal symbol of a NMOS: drain, gate, body, and source. Now I also know that in order to eliminate body effect, I need to connect my body terminal to source terminal. Okay, so that I will have VBS equal to 0. This is the first fact. Now if I want to plot the IV characteristics of this MOSFET, I have to redraw it like this. Drain, body, short it to the source, source, gate. Now this is my V1, that is gate to source. Similarly, now I have my VDS. Let me say it is V2. Okay, and this is connected to ground. So see here, these are all ground points. Okay, I will define that this is my node 2 and this is my node 1, and I have to find out the current flowing through this branch. Okay, this branch I have to find the current, and because I want a family of curves, that is why I have to vary this. Okay, so basically V1 is equal to 5 volts, but I am going to vary it from 0 to 5 and let my V2 be equal to 10 volts. Okay, now understand one thing, that whenever you want to do spice modeling of MOSFET, at that time you have to give some name here. Okay, so we have to give a name. Let the name of my device be N1. Okay, so N1 is the name of the device. Okay, we have node number 2, we have node number 1, we have the drain side source V2 equal to 10 volts, we have V1 and 5 volts is there, and we have ground, ground and ground. Now please read this thing. Drain is connected to node 2, body and source are shorted together, and source is connected to ground. Gate is connected to node number 1. Is it clear? So we should know that to which nodes all the MOSFET terminals are connected. So drain connected to 2, body and source both of them connected to ground, gate is connected to 1. Is it okay? Now we have to implement all the 5 steps which we defined here. But please understand one thing, you need to know what is the syntax for defining a MOSFET. The syntax is like this. It is like this. Just like I said that the alphabet V indicates to the spice engine that it is a voltage or a voltage source. Similarly, the syntax for MOSFET is like this. Syntax for defining MOSFET. It is alphabet M and immediately concatenate device name, then drain, gate, source, body. Then this is called as library link name, and then what is the value of width in micrometers, space, length equal to micrometers. Okay, so in our case device name is N1, drain connected to node 2, gate connected to node 1, source and body connected to ground. Let the library link name in our case be N underscore MOS. Okay, you're confused. So library link name in our case is can be, so it is user defined, you can say anything N underscore MOS, that is my choice. So how do I define it? I define the MOSFET like this. I say M N1, then I will say drain is connected to node number 2. So I will say 2, gate is connected to 1, source is connected to ground, body connected to ground, library link name N underscore MOS, W equal to 4U, L equal to 2U. We have defined the MOSFET completely now. This is how you define it. It's okay. Now this is the component. So this is step number 1, that is define all the components, active and passive. Now what we do is we define V1 and V2. So V1 and V2 are DC sources. Just like before, I can say I can say V1 connected between 1 ground and the value is 5. Similarly, I will say V2 connected between 2 and ground, value is 10. Okay, step number 2 is also over now. Okay, we have defined the sources also. Now we go here and we define the type of analysis to be performed. Okay, so because I want a family of curves, I am going to vary the VGS from 0 to 5 in steps of 1 volt. So I will have 5 curves now. Okay, so I will say dot DC vary V1. So it is like this: initial value space final value space step size. So I will say I have to vary V1 from 0 to 5 in steps of 1 volt. So we'll have 5 curves. VGS equal to 0, 1, 2, 3, 4 and 5. We'll have 5 curves, 6 curves basically. Similarly, because IDS versus VDS, I have to vary VDS and find IDS. So IDS, VDS also has to be varied. So this is also to be varied. So we will vary this from 0 to 10 volts in steps of 0.5 volts. So we'll have 20 steps from 0 to 10. So I will also say again dot DC vary V2 from 0 to 10 in steps of 0.5. So we'll have 20 different values of VDS from 0 to 10, and we'll have 5 values of V1 from 0 to 5. So this is what we have defined the kind of analysis I have to do. Step number 3 is over. Now we have to include the model files. As I told you, we already written the syntax. So dot model space library link name space library underscore name level equal to 1 to 49. So we will write down dot model. Our library link name is here. Library link name is here. Sorry. NMOS. Same thing I have to copy here. So I say dot model. My library link name is n underscore mos, and the mathematical model of an NMOS is actually written in the library whose name is NMOS. So it is like this. It is we'll highlight it later. NMOS, and I will say level equal to, initially let me say it is 1. So I have also included the model file here. So here understand one thing, which are the keywords. M is a keyword, ground, W, L is a keyword. Okay, so I will remove this because n underscore mos is user defined. Okay, so I will say, let me, okay, yeah, V keywords, ground keywords, dot DC is keyword, dot model is a keyword, NMOS is a keyword, level is a keyword, and this is user defined. Okay, now last is we want to define what kind of output we want. So last step is this. We can say like this, dot print. Now I want to find out the current. So this is IDS. So this is IDS. So please understand one thing, that IDS is flowing from V2 through the device N1, right? So I have to write down like this, dot print. What should I print? It should display me the current waveform through the MOSFET N1, and the current is flowing through V2. This is how it is. Okay. So MN1 indicates the MOSFET whose name is N1, and the current is actually coming from VDD and is flowing through the device. So again, if you want to highlight, you can highlight this like this. Dot print is again a keyword, current is a keyword, M is a keyword, remaining else is user defined. This is all user defined things. Okay. Yeah. So family of course, and this will give me IDS versus VDS, 20 values. Okay. So I told you, yeah. Is the UI of Microwind visible here? Yes.
Yes, sir.
Yeah. So I was telling you about secondary order IV effects. This is one thing which I do not know if you have explored. If you're not explored, this is an additional information for you. If you go to Microwind in the icon bar, there is this particular thing which is called as simulate MOS characteristics, right? So when I click this, immediately it plots something for me. Now see, this is a very wonderful kind of a dialog box. You will come to know. See here. So if you go down, so you have to select the device, right? So PMOS and NMOS. So let us see what is the current generation capacity between NMOS and PMOS for the same W by L ratio. See, now I will select NMOS here, and I will have different W by L ratios. So my first W by L ratio is 1 micron upon 0.1. So size is 10. So the first is NMOS with size 10. Second is NMOS with a size 1. Third is an NMOS with size 0.2. And fourth is an NMOS with size 2. Okay. So if suppose I take an NMOS, so we have to see that how the current carrying ability of a MOSFET is, it is a function of W by L ratio. So the first case W by L ratio is 10. So for 10, I am getting this. See, what is the maximum value of current I am having? So the maximum value of current, now because it is an NMOS, as VGS increases, IDS will increase. So you see here, the VGS is increasing from 0 to 0.2 to 0.4. So as VGS is increasing, IDS is increasing. So for maximum value of IDS, I'm sorry, for the maximum value of VGS, which is equal to VDD 0.2, the current is touching 1250 microamperes. Okay. Now see, level 1, level 3 and BSIM 4. So for level 1, that is the most preliminary we see here. So for level 1 simulation, W by L ratio is 10. And for NMOS, I say that for maximum value of VGS, the current is 6 milliamperes. Okay, 6 milliamperes. Now, when I say level 3, you are seeing here the current is becoming constant. You see here it is having a tilt because the channel length modulation parameter lambda is getting multiplied. So in the saturation region for small channel, short channel MOSFETs, we have IDSS is equal to IDS equal to IDS sat into 1 plus lambda VDS. See what is BSIM 4? See, BSIM 4 is the highest level of modeling. And we see here, we are able to see that the current is not remaining constant in pinch off region. That means BSIM 4 gives you a reflection of channel length modulation. Level 3 not that much, level 1 not at all. See here, so here for W by L ratio equal to 10 for 90 nanometer foundry, we see that when VGS is maximum at 1.2, the current is 6 milliamperes. Let us go and say that the size has now reduced from 10 to 1. You see here, what was the value here? When the size of NMOS is 10, then ID max is 6 milliampere, that is 6000 microamperes. Now the size is 1, and you see here for same value of VGS max, the current is 600 microamperes. You see here from 6000 microamperes to 600 microamperes. Immediately that means what? Current is directly proportional to W by L ratio. Now go and say the size is equal to 0.2. You see the current? The current has reduced to 150. So we are clearly able to see that the current flowing through any MOSFET is proportional to W by L ratio. And see here, we have 2. So in 2, I am getting the current as 1200. Right? So as W by L ratio changes, the current through the MOSFET also changes. Now, level 3, BSIM 4. So channel length modulation can be seen here. The first observation we have is that the maximum current flowing through MOSFET is directly proportional to its size, that is W by L ratio. Second thing, when I increase the level of modeling from level 1 to level 3 to BCM 4, I am able to see channel length modulation effect. Now, comparison between PMOS current and NMOS current. Let us create identical conditions for MOSFETs. So select NMOS, select size equal to 10, and we see for level 1, so the maximum current flowing through NMOS with size equal to 10 for VGS max equal to 1.2 is 6000 microamperes. Let me click PMOS here, and in PMOS let me select the same specifications. For PMOS I am selecting size equal to 10 and level 1. You see here it is 2750 microamperes. Note this. So the maximum current generated by an NMOS is 6000 microamperes versus PMOS, which is generating 2750 microamperes. Let us see what is the multiplication factor. So I have NMOS current 6000 divided by 2750. Value is 2.18. Students, this is important to note. That is NMOS device for the same geometric dimensions and operating conditions generates 2.18 times more current than PMOS, because the current is also a function of mobility of charge carriers. Okay, remember this thing, that NMOS device is producing 2.18 times the current produced by PMOS of identical dimensions and under identical electrical operating conditions, because the mobility of an electron is said to be 2 to 3 times that of a MOSFET of a PMOS. I repeat, because the mobility of an electron is 2 to 3 times the mobility of a hole. That is why this difference in mobility is reflected in the form of the maximum current which is produced by an NMOS device. In other words, we can say that because NMOS produces 2 times the current produced by a PMOS, we say that PMOS device offers half the resistance of a PMOS. Okay, so our observations were like this, that for WP by LP is WN by LN is 1 micrometers upon 0.1 micrometers is equal to 10. For mod of VGS equal to 1.2 volts, we found that IDSN max, that is a maximum current produced by NMOS, is coming out to be 6000 microamperes, while the drain to source current of a PMOS maximum is 2750 microamperes, and we find that IDSN max is approximately 2 times IDS P max, because the mobility of an electron is approximately 2 times the mobility of holes. Okay, yes, this was an important thing which I wanted to show you. Good, it was covered today.